All right, so let's say that your task is to predict house prices in California. This toy problem comes from the California housing dataset from sklearn, the Python library. And the distribution of true home values looks like this. It's skewed normal with this big, with like a bunch of outliers kind of at the end, which would be kind of hard for a network to learn. And you can kind of normalize it, just some sort of data cleaning. Those outliers are still there, but this is the thing that we're predicting. And then we convert it to back to the normal way of viewing it, just so that when we compare loss functions, when we compare the performance of networks using different loss functions, we're going to compare them on this graph because it's more intuitive, because the x-axis is something, something actually real, median home prices, instead of, oh, this axis is incorrectly named. But no. Um, so the standard way of doing it is mean squared error, and the formula for that is over n samples, your guess for that value minus the true value for that sample squared, sum it up. And so let's say that these are your true home prices. 1, 2, 3. And this would be a $0 home down here. And let's say that your guesses for these home prices are this, this, and this. Then when you plot the residuals of this, it looks like this is 0 error. When you plot the residuals, it looks like this, this, this. And mean squared error, when you use that as your loss function, you try to get all of the errors to go to 0. Which is, that's intuitive because you want these predictions to go to their true values. But what if instead of that, we just wanted all the predictions to go to the mean prediction value? So we just want this to go here. That can stay where it is. And we want this to go here. As you can see, when you do that, the guesses have less distance that they need to move. So it might be easier to train the network to do that. That's a little bit of the intuition. So what that looks like over here is this one just stays where it is, but this one needs to move up a little to like here, let's say. And this one needs to move down a little to like here. And the idea is that these new guesses are all the same distance. Oh, I forgot to do this one. Oh yeah, because this one just stays the same, that's why. These new guesses are all the same distance. These 3 distances are all the same. And so then, as kind of like a post-processing thing, after you train your network to have consistent error, you just correct for that error afterwards. And it's a little bit more complicated than just trying to make the error go to 0 from the beginning. But it might make it easier for the network to learn. And so I call this standard loss because you're trying to minimize the standard deviation of the residuals. And the formula for that is over n samples, the guess for that sample minus the average error. So this is the ground truth for the residual, whereas this is the average that we're trying to go to. So the error is, the error is the distance from here to here versus the distance from here to here. This is that. And this is that. And so what that looks like in code is, oh yeah, square it. What that looks like in code is just a very simple, the residuals. This loss function is just you get the residuals, and then you try to minimize the standard deviation of the residuals. And when I did this, I did 3 rounds of this. I trained the same models with 2 different loss functions. And when it was trained with the mean squared error loss function, the root mean squared error was $57,000. And when it was trained with this new loss function, the root mean squared error at the end of training was $50,000. And this is like on the validation set, not the training set or anything. And so with the new loss function, we were able to get a loss that was 13% smaller. So less loss is good. And what that looks like graphically is this big comparison of everything. So the blue is the ground truth. That was what I showed you at the beginning. This was the thing that was going to be hard for the model to do. And when you use mean squared error, industry standard sort of thing, you get something that mostly fits the distribution, but then it kind of falls off here. It's kind of hard to see because they're all overlapping, but the orange falls off here and doesn't predict like anything really beyond 4.5, beyond $450,000. But the new loss function, is just as good over here, but then it also does a slightly better job. It's a little bit closer to predicting this big outlier section over here. And this is consistent over all 3 cases. Like this is just one of the test runs that I plotted, but over all 3 test runs, I looked at the graphs and they all look like this, where mean squared error drops off fast, and then standard loss does a little bit better job of predicting this bimodal spike over here. I think that's it. Yeah. Yeah, so just, reduce the standard deviation of the residuals. That's the best way of putting it. That's that.